Let's get started. We're going to talk about SOLIDWORKS fatigue analysis in this webinar. Let's talk about fatigue itself. How does fatigue happens and what is fatigue? Basically, when you apply a load, we know how to do simulation obviously. When you apply a load to a component and you get the stresses for that component, if the stresses are below the yield stress of the material, that particular part is not going to fail. Well, what happens if you apply the same load repetitively to that model? What's going to happen is that eventually that model, that part, that material is going to get tired. Cracks are going to get developed throughout the model, and eventually fatigue is going to happen. So for fatigue to happen, your stress, your maximum stress of the component, when you apply the load on it, it could be way below your yield stress. But when you repetitively apply that load to the model, fatigue can happen. When we talk about fatigue, we have to know that we have two different loading types in a fatigue analysis: constant amplitude loading and variable amplitude loading. What's the difference? In a constant amplitude loading, your load is steady. You can apply the load in a few different ways. The most famous and more common ways that you apply a constant amplitude loading is that you can apply the load on and off. Like you can apply the load, let go, apply the load, let go. Or you can pull and push the component. We're going to talk about that shortly. Within the variable amplitude loading, within the constant amplitude loading, the load doesn't vary. But within variable amplitude loading, the load is going to vary with time. And you're going to, like a good example would be a vibration on a suspension system. To analyze a suspension system that is being vibrated, you need to do a variable amplitude loading fatigue analysis. Within this webinar, we're going to just talk about constant amplitude loading fatigue analysis. When you talk about constant amplitude loading, you have to know a few basics about this kind of fatigue analysis. Let's jump to these basics and actually let's talk about them. In the picture that you can see, I have a stress and time diagram that shows the stress time, the change of stress based on time within a constant amplitude loading. You can see within this diagram you have the stress alternative being shown here, minimum stress, mean stress, and maximum stress. As you can see, the mean stress is the average of maximum and minimum stresses. All right, very simple. But what do we know? Why do we actually need this diagram? Having this diagram and having the alternative stress, basically the alternative stress is the stress that alternates throughout the process of fatigue analysis when we apply the load to our component. This diagram is referred as a reversed diagram. We're going to talk about that shortly. Here are some of the most important terminologies that you need to know for that diagram. The alternative stress, the mean stress, and a stress ratio. When you do a fatigue analysis, you have to define the stress ratio for your model. A stress ratio, as you can see in this slide, is S minimum divided by S maximum stress, minimum stress divided by maximum stress for the model. When you talk about the stress ratio, the most two typical common cases are zero-based and fully reversed. So when you do a fatigue analysis, I'm going to show you that in a model. When you do a fatigue analysis, you can say this fatigue analysis is zero-based or is fully reversed. Or if it is not either of them, you can define the ratio. Obviously, this is something that you as an engineer have to calculate. The diagram for the zero-based and reversed loading histories are actually shown in this slide. What does it mean when I say the loading is zero-based? It means that when I apply the load, I push the component, I apply a load to a component, and then I let go. So the minimum stress is actually zero, as you can see here. And the maximum stress is the maximum stress based on the maximum load that I apply to the component. So the stress is going to fluctuate like this. But as you can see, the maximum stress is always the same throughout the model. So my load is not fluctuating. The load is the same. That's why it's a constant amplitude loading. As you can see in this diagram, you have a view of a fully reversed loading history. A fully reversed loading history means that I apply my load. I push, let's assume, a bar. I push the bar in one direction and I then pull it back in the opposite direction. So I have the same positive and negative stresses on that component. That's when we say this loading history is fully reversed. But what if my maximum and minimum stresses don't meet these requirements? In that scenario, you have to, as mentioned, you have to calculate the stress ratio and then apply it in your fatigue analysis. When you want to do a fatigue analysis, so we just learned that you have to know what your stress ratio is. When we do a fatigue analysis within the properties of your material, you have to define something else as well, which we call the SN curve. But what is an SN curve? SN curve is the stress. This column represents the stress that causes fatigue in your material. The N side defines the number of cycles that causes fatigue. So basically, by looking at this diagram, I can tell at what cycle what is going to be my fatigue stress. As a case in point, in this diagram, you can see if I apply this many cycles with this much stress, the part is going to fail by fatigue. So when I talk about fatigue, there is a number of cycles involved in the process. When I talk about constant amplitude loading fatigue analysis, I need to know how many cycles. So the number of cycles is really important in a fatigue analysis. As a case in point, in this case, I'm going to show you a case study of a bicycle paddle. And we're going to talk about the number of cycles and the SN curve in that paddle. What about the variable amplitude loading? If you have a variable amplitude loading fatigue analysis, you have to know your loading history. It could be your stress time history. As you can see, there's an example of a loading history that is shown in this diagram. There are many ways to calculate this. Basically, you have to examine your model to get this diagram. Well, you can see the stress fluctuates rapidly throughout the process, and it doesn't look anything like the constant amplitude loading. I'm going to show you a case study of a bicycle paddle. I've got three different designs of a bicycle paddle, and I want to know which one withstands 7 million cycles of a specific load. The load obviously doesn't fail the model initially. The stress I get from that specific load is below my yield stress. I basically want to know which crank is going to fail the model after applying 300-pound load on this component and after 7 million cycles. So I have a target in mind, 7 million cycles. I want this paddle to work for 7 million cycles when I apply 300 pounds load on it. Let's have a look at it within SOLIDWORKS. Let me open up SOLIDWORKS for you guys. Just bear with me for a second. There we go. All right. Let's have a look at this model. This is a paddle. It has a series of configurations, as you can see. These are the configurations, these are the different models I want to analyze using fatigue analysis. When I talk about fatigue analysis, you have to analyze your model by an static study first. So you need to have an initial study on your model before you do your fatigue analysis. Let's have a look at that. So on this model, I have an static study. If I go to the static study here, I've already created an static study for it. You can see the material has been defined for this model. A global bonded contact set was defined for this assembly. A series of fixtures, fixed hinges have been defined for these holes. And this hole at the back, this extrude at the back, to fix the component properly in this space. The external load has been applied to this surface. And you can see a series of mesh controls have been applied to the model. After running the analysis, I can get the stress results. You can see the stress result is 215 megapascal, which is below the 275 yield strength of the material. So this part with this load is not actually failing. But what happens if I apply this load with 7 million cycles? To figure that out, I have to do a fatigue study. So when you go to new study, you can select to run a fatigue analysis. When I select fatigue analysis, I have to define whether it's a constant amplitude or variable amplitude loading. This is a constant amplitude loading. After creating the fatigue study, you'll be provided with such a window. You're not going to define the fixtures and contact sets anymore. It's going to read all of them from the initial static study that you had. Well, one important thing within a fatigue study is that when you apply your material, it will take you to the fatigue SN curve dialog box, where you have to define your SN curve and tell SOLIDWORKS at how many cycles for that specific material, at how many cycles the fatigue stress happens. So you basically have to say at 1,000 cycles, the fatigue stress is this much. At 5,000 cycles, the fatigue stress is this much. So you have to have this information prior to do your fatigue analysis. When you define your SN curve, so this information is not stored in the database of materials in SOLIDWORKS. You have to insert it yourself for most of the materials. After inserting the SN curve, you have to define a loading event for the material. Do you remember those loading events? Fully reversible. Let me show it on these slides. These two, zero base and fully reversible. This is basically what you have to define as an event within your simulation. But how to define a loading event? You have a loading tab here. If I right click on it, I can select add event. I've already created an event here. Let's just edit it and see what I have defined within it. You have to define the number of cycles that you want to apply to this model. We have set 7 million cycles, and you have to know what's the loading type. The loading history type in this scenario is zero based, meaning that I apply the load, then I stop applying the load. I apply the load again. I apply the load 7 million times and I stop. So it's a zero based loading cycle. Within the study tab, you have to select your initial study that you want to run this fatigue analysis based on it. Static 1. I'm not going to change the scale. If you have an environment, like let's say you have salt in the environment, which is going to even reduce your material resistance even more, you have to play with these scales. I encourage you to read some articles about this and figure out exactly what scale is proper for your environments. You have to do some hand calculations for that. So when you define the event, the loading event, all you have to do is to run the analysis. But when you run the fatigue analysis, there are certain results that you can get from the fatigue analysis. The most two important ones are damage and life. Let's analyze these two results. When I have a look at the damage, I can see the maximum damage happens about here, and it's 176.8%. So what does this mean? It means that the damage was done 176%. It's 76% more than 100%. So obviously, this part is going to fail. Where? Here. In the blue area, the percentage changes from 0.7 to 15%. What does it mean when I say 15% of damage is going to happen in this area? It means that after 7 million cycles, 15% of the life of this blue area is consumed. But at the same time, 176% of the life of this area is consumed. So this part is going to fail way before 7 million cycles in this area. But how should I know after how many cycles it fails? That's where a life result comes in handy. So when I look at the life result, I can see the minimum number of cycles is 3,900,000 almost. So this area fails after 3.9 million cycles, which is way below my 7 million cycles. So I can conclude this is not a good design. Even though my maximum stress is below my maximum stress for this design is below the yield stress, I can conclude that it's not going to last for 7 million cycles. So I change the model. I use my second configuration. And I run the same static study on that configuration. Let's activate this configuration. And let's have a look at it. You can see the same load has been applied to this model, the same contact set, the same fixtures, the same force, the same mesh controls. Let's have a look at the results. When I look at the stress result, you can see the stress result is quite different. The maximum stress is 198 megapascal, and it's happening here at the back of this component. And 198 is obviously below my yield strength. So I can conclude that this stress, if this load, if applied once, is not going to fail the model. But what if I apply it 7 million times? Let's do another fatigue study. If I open my fatigue analysis, you can see it has the same settings. If I go to the material properties, it has the same SN curve. I haven't changed the material, so the SN curve is going to be the same. Look at the event. Within the event, 7 million cycles are being applied to the model. But this time, for the study, I'm using the static design number 2, this study. The static study appropriate for this configuration. So I'm basically saying I want to apply 7 million cycles of that specific load and that specific stress for this specific configuration, and I want to know what happens. Let's have a look at the damage results. If I have a look at the damage result, I can see the maximum damage is 51.3%, which is great. It's not reaching the 100%. So this part is not, the fatigue is not happening in this part after 7 million cycles. What happens after 7 million cycles? After 7 million cycles, 51% of the life of this component has been consumed. So I can conclude that this part almost goes for 13 million cycles. If I have a look at the results for life, you can see the red area, the minimum number of cycles that this component can go through is 13.6 million cycles. So after 13.6 million cycles, this component is going to fail by fatigue in this area. So this design actually meets our requirements. It goes beyond 7 million cycles and it goes to 13.6 million cycles. So this is the design that I'm after. But let's analyze the last configuration that we had for this model. We need to do an static study on that specific configuration as well. Let's have a look at it. When I do an static study, I can see the maximum stress on this specific configuration happens in this area and is still below the yield strength of the material. But I want to know what happens after 7 million cycles. Let's have a look at the fatigue study. Again, the material is the same, so the SN curve doesn't change in this study. Let's look at the event. 7 million cycles of this study, static design 3, which was for this configuration. When I have a look at the damage results, I can see the maximum damage is 462%. So this part fails miserably by fatigue. After how many cycles? After 1.5 million cycles. So this is the weakest design that we have. Only after 1.5 million cycles, this part is going to fail here. So cracks are going to develop on the surface of this model in this area after 1.5 million cycles, and it's going to fail. So fatigue analysis basically is going to enable me to figure out whether the load is going to fail the model or not. So just knowing that by applying your load once on your model and getting the maximum stress below your yield strength is not good enough, because that part could still fail if you apply the same load repetitively onto that component. To find out how many cycles is needed to cause a fatigue, you have to do a fatigue study. This brings me to these last couple of slides, which are going to compare the results. Let's have a look at this. So design number 1, it didn't meet our requirements. But design number 2 was a proper configuration. It went through almost 14 million cycles. And design number 3 was the weakest. It only went through 1.3 million cycles. This brings me to the end of this webinar. If you have any questions, you can type it in the chat area and I will be more than happy to answer your questions. Please feel free to shoot me any questions in the chat area. and I will do my best to answer them. Alright guys, if you have any questions, please feel free to ask in the chat area. Alright guys, I haven't received any questions. So let's do a wrap up on fatigue analysis and we're going to end the webinar. I've got a question here. Does SOLIDWORKS handle crack growth models as well for damage tolerance? It doesn't tell you how much crack you're going to get in the model. What you can analyze is the damage. Let's have a look at the results that we get from a fatigue study. So if I right click on the results and define a fatigue result, you can define the life, damage, load factor, and bioaccelerated indicator. The damage and life are the most popular ones to look at. It won't tell you how big a crack is going to be or how many cracks are going to happen. It will tell you how many cycles of that load is going to cause a fatigue. Basically, when you get the initial crack, that's about it. Your part is going to fail. And that's when SOLIDWORKS tells you, okay, after this many cycles, a crack is going to get developed on the surface of the model. So basically, looking at the damage or life results of the model, you can get the same result. I hope this answers your question. If not, please shoot me another question. I'm going to do a quick recap of this discussion that we had. Right, let me bring up the slides. There we go. So when you talk about, we learned that when we talk about fatigue analysis, we have constant amplitude loading and variable amplitude loading. This really depends on the type of the load you apply to the model. If your load doesn't change radically, if your maximum stress and minimum stresses are maintained throughout the process of different cycles of loading, it will be a constant amplitude loading. But if your load changes rapidly, your maximum and minimum stresses are different in each cycle of load, that will be a variable amplitude loading, basically. Let me show you these slides. All right. We have learned about the terminologies within constant amplitude loading. The stress time curve, which defines the stress ratio. So you have to know the alternative stress, the minimum stress, the mean stress, and maximum stress to be able to calculate different terminologies for your fatigue study. The main one is the stress ratio, which can be calculated from dividing S minimum to S maximum, minimum stress to maximum stress. These are the terminologies for constant amplitude loading, again, just for constant amplitude loading. The main two typical loading histories are zero-based and fully reversible. Zero-based means that you apply the load, you get your maximum stress based on your load, and you let go. So the minimum stress is zero, which causes the stress ratio to become zero. In a fully reversible scenario, in a fully reversible loading history, you apply the load, you push the component, and then you pull the component back. So you have a maximum stress, and the minimum stress is right opposite the maximum stress. which results in this ratio to be -1. If the maximum stress and minimum stresses don't fall in these two categories, you have to calculate your stress ratio, and you have to define it within your simulation, within your fatigue analysis when you define an event. So if I have a look at my fatigue analysis and go to my event, you can see I have the ability to define my loading ratio right here. So if your loading doesn't fall between zero base or fully reversible, you have to calculate the ratio. Let's go back to these slides. The SN curve is a very important part of the fatigue analysis. You have to know, and you have to know the SN curve for the material that you use for the fatigue analysis, basically. The SN curve is going to give you the information about at what cycle, at what number of cycle, what fatigue stress is going to cause the fatigue. You get the SN curve from testing the materials. I believe you can download some information from some material databases online. You can purchase some information, or if your material is really specific, you have developed the material yourself, you have to do a series of tests. And again, if your loading is if your fatigue analysis is variable amplitude loading, you have to have the load case for your simulation. Let's say you have a suspension system and you are applying vibration to this suspension system. You have to have the stress time diagram for that specific load, for those specific loads, for that specific vibration that you apply to that suspension. Again, it can be calculated from testings on your specific designs. I hope this webinar was helpful for you guys to get a better understanding of fatigue analysis. If you need to do fatigue simulations, you would be required to use SOLIDWORKS Simulation Professional. With any SOLIDWORKS CAD packages, it could work. But for a simulation package, you need to use the professional package to be able to do a fatigue analysis. Again, I hope this session was helpful. If you have any inquiries, you can email me back. My email address was within the invitation for this webinar. I hope to see you guys in the next webinars. Please let me know if you have any questions in future. You can always email me. I will do my best to respond back. Hope you guys have a good day, and I'll speak to you soon. Enjoy your day. Bye.